Hi everyone, I would like to look at the problem of fluid flow around a circular cylinder. And let's start with the potential flow about a circular cylinder, and then hopefully that's going to motivate us to move on to the real fluids, i.e. like fluids with viscosity as they pass over a circular cylinder. So again, the problem is I have a cylinder and I'm looking from the, well, let's say side or from the top anyways, and then there's a uniform background flow at infinity, and this flow comes toward the cylinder, and we know what we expect to get, right? So there's going to be a stagnation point here, and then streamlines above the cylinder is going to be like this, right? At least for the potential flow, something like that, right? And then the same thing on the bottom side. It should be kind of symmetric, right? Okay, so the first question is, well, we want to see if we can get this from potential flow theory. And well, there's a uniform flow at infinity, so definitely we're going to have a uniform flow at infinity. And potential or stream function of the uniform flow now needs to be added to something else. So one suggestion is let's do a doublet. Now, what's a doublet? Just a reminder, doublet is a source and a sink, right? A source and a sink. Now, the strength of the source is equal to the strength of the sink. And then we know the velocity potential. I can bring it just here. Of the system or streamlines. Well, a source is sending stuff out like this, and sink is basically drawing everything in. So the source is sending out, sink is drawing stuff, streamlines or fluid particles in. And as a result, what's going to happen is that, well, we have things going from here to here, here to here. And then, of course, this one is going out, this one is going out. So we can expect that we get something like this, right? So eventually, this is the kind of streamlines we're going to get. Now, a doublet is an extreme case. Doublet is an extreme case where the source and sink, and they are extremely close to each other, and their strength is also extremely large. So if the strength of the source and sink is m and their distance is a, well, in the case of a doublet, we have the limiting case when m goes to infinity, a goes to 0, such that the multiplication is a constant. We call it like a k times pi. So pi is just a pi 3.14, and k later on we're going to call it, or you've called it, the strength of the doublet. All right. Good. So let's add now, it's just a review of what a doublet is. Let's add a doublet to a uniform flow and see what happens. Again, I don't know what's going to happen. So I have a doublet here, all right? All right, very close, really 0. And then a stream, right? Let's first physically guess what picture we're going to get. So as I said, the doublet itself has this kind of velocity potential, the streamlines, right? And then this is a source sending things out, and this is a sink drawing things in. So I expect that at some point the incident velocity with velocity u kind of balances the velocity along the center line. So there's going to be a stagnation point somewhere. All right, and then what happens is now this is a stagnation point, and looking at the streamlines here, it is reasonable to expect that a streamline is going to separate from the center line and go there. Now, what's going to happen next is not clear, but again, what I expect is at some point it's going to go back to the center line because things need to get back to the sink here, right? So it could be something like an ellipsoid or even a sphere, right? But we don't know. This is just our guess. So what we're gonna do is we're gonna superpose a uniform stream and a doublet. And then we have to show whether this is going to be flow about a circular cylinder or not, right? And we're going to do that. Okay, so let's get started by reminding ourselves that for a uniform flow, and I can just draw a coordinate system here. So we have a uniform flow. This is the x-axis. This is the y-axis. And let's assume our uniform flow is in the x direction with a speed u. So therefore, u, or horizontal velocity, is capital U, and v is 0. For this flow field, we know that phi is equal to ux, and psi is equal to uy. Okay. Now, for a doublet placed at the origin, we know that phi is equal to k cosine theta divided by r, and psi is negative k over r sine theta. Okay, good. So as I said, we're gonna superpose these two, and we can pick either the velocity potential or streamlines, stream function, right? Either works, right? Let's go with the stream function. All right, so therefore, the total psi is going to be equal to psi of a uniform flow plus psi of a doublet, which is equal to, well, for this case, uy minus k over r sine theta. And it's okay if one part is written in Cartesian coordinate and the other part is in polar coordinate, but we know the relationship between the two, right? So x is r cosine theta and y is r sine theta. So you can either substitute r and theta from the second expression in terms of x and y, or y in terms of r and theta. So specifically, if you want to write it in polar coordinate, therefore this is going to be ur sine theta minus k over r sine theta, or I can write it as ur minus k over r sine theta. Okay. Now, let's calculate velocity in the r direction and velocity in the theta direction. So Vr is equal to 1 over r d psi d theta, and v theta in terms of the stream function is equal to minus d psi dr. Okay, so substituting from the above, this is going to be 1 over r d psi d theta is ur minus k over r cosine theta. And v theta is going to be minus ur, it's going to be sine theta, because say ddr, and that's going to be u minus or plus k over r squared. Okay, now let's see, and again, I'm not claiming anything yet. Let's see under what condition Vr is equal to 0. So Vr equal to 0 gives us the condition that ur minus k over r is equal to 0. And from here, we conclude that r2, excuse me, is equal to k over u. And therefore, r is square root of k over u. So, and this is interesting because it says at a constant r equal to square root of k over u, and k is given as the strength of the doublet, u is the external, the uniform flow velocity. At that r, right, velocity in the r direction is 0. Okay, so there is a radius. So I can draw a circle here. There's a radius, constant radius from the center, across which there is no velocity in the r direction. All right, so what it means is that everything is tangential, right? I don't know what the velocity is. It can be in any direction, right? But I know that there is no component in the radial direction. So therefore, and this is a streamline, if I substitute this with a rigid boundary, and I can do that in a potential flow if we have slip boundary condition, then this is going to be a flow field about a circular cylinder, right? Because again, this boundary of a cylinder has no radial velocity. Okay, and it does have a velocity in the theta direction, but it doesn't have any velocity in the r direction. So that's an acceptable solution. So that's why we come to the conclusion that, well, our first guess of superposing a uniform flow with a doublet is a good guess. We got the flow field about a circular cylinder. All right, now the next is let's calculate how much force is exerted on the cylinder. All right, so maybe I can draw a line here. And then here the objective is to calculate the force on the cylinder in potential flow. So we're not considering any viscosity. It's irrotational and incompressible fluid flow. Okay, so in potential flow, because of irrotationality, we know that Bernoulli's equation is valid between any 2 points. So basically P plus 1/2 rho V squared plus rho GZ is equal to constant. Now, our problem is a 2D problem. It can be in a XY plane, not in a vertical direction. So, or we can just say we neglect the effect of gravity. So the third term goes away. So this we don't take the up and down motion into account. Now, yes, if it's a horizontal cylinder and we have gravitational acceleration in this direction, now we have to definitely take rho gz into account, and there's going to be buoyancy and all kind of things, and hydrodynamic pressure and so on the cylinder. But let's assume that's not the case. Basically, xy is a horizontal plane, and the cylinder is kind of vertical. It's like a bridge column or a tower, right? And there's a wind is blowing in the horizontal direction, and we want to calculate the force on that. All right, so pressure plus 1/2 rho V squared is equal to constant everywhere, right? Including at infinity. So what do we have at infinity? Well, we know that at infinity we have P atmospheric plus 1/2 rho U squared. That's a velocity of the uniform flow. And that has to be equal to our same constant everywhere in the domain, right? Now we can work with the gauge pressure. So I can set the atmospheric pressure equal to 0. So all pressure are gauge. So therefore the constant is equal to 1/2 rho U squared. And we can simply stick to that. Or I mean, you can do either way. If you don't want to set it equal to 0, that's going to be PA plus 1/2 rho U squared. All right. So basically everywhere in our domain, what we have is pressure plus 1/2 rho V squared. Now this is pressure at any random point, and that's velocity at that random point. That has to be equal to 1/2 rho U squared, right? Or pressure is equal to 1/2 rho times U2 minus V2. Okay, now clearly if V velocity at that location is higher than U, then pressure is going to be less than 0. This is a gauge pressure, so it means that pressure is less than pressure at infinity. If V is less than U, it means that pressure is higher than pressure at infinity. Okay, now we want to calculate. Now we have the pressure, expression for pressure, and we have expression for velocity. Well, at least on the cylinder, velocity in the r direction is 0, and velocity in the theta direction is given by this expression. So it should be easy to just simply go ahead and integrate the pressure along the cylinder and calculate the total force. All right, so this is our x-axis, this is our y-axis. So if I have pressure here at any given point, and then that point is highlighted by theta and r equal to a, so then the pressure results in a force normal to the surface. So that's going to be P ds. ds is the length of this little arc, which we know is equal to r d theta. So that's the force, but now we're interested in the vertical component of the force. So if this is P ds, this is a total force. I have to decompose this force, and again, this is theta. So the vertical component is P ds. Maybe I draw it with a different color. The vertical component is P ds times sine theta. And then the horizontal component, or the force in the x direction, is P ds times cosine theta. All right, and then we have to integrate this from theta 0 to 2 pi. Let's quickly do that. That's not difficult. So the force in the y direction, let's say y hat, that's going to be integral of I can say just substitute here this component. So that's going to be integral of P ds sine theta. All right. And that's it. So, and then from theta equal to 0 to theta equal to 2 pi, the y component of the force, right? Because of the way that we define P is in the negative direction, I'll put the negative sign here. That doesn't matter. So as I said, that's going to be minus integral from 0 to 2 pi of, well, pressure is this expression, 1/2 rho U2 minus V2, that's U. ds is r d theta, and then I'm going to have a sine theta here. Okay. Okay, that's equal to negative 1/2 rho. I'll bring the 1/2 rho out. Integral from 0 to 2 pi. Well, U2 is just a constant minus V2. So V2 has two components. So V2 is VR2 plus V theta 2, but we know on the cylinder VR is 0, so that's going to be V theta to the power 2. V theta is given here, so all I need to do is just to put minus sine 2 theta times U plus K over, and R is A, right? That A that we derived here. I just put A here. A2, that's V theta 2, good. Times, again, R is A, I can just bring it outside the integral, sine theta d theta. So the good thing is we don't, I mean, it's a very simple integration. That's going to be negative 1/2 rho A integral from 0 to 2 pi r U2 sine theta d theta minus integral from 0 to 2 pi of, and everything is inside the bracket here, U plus K over A squared, this is a constant, times sine 3 theta, this is sine 2 times this sine, d theta. What's the integral of sine theta d theta? What we can do is just plot sine theta, and sine theta is like this, going from 0 to 2 pi, the total area of sine theta is 0, so that integral is 0. And how about sine 3 theta d theta? Again, if you plot sine 3 theta, it's a symmetric curve. It's going to be a little different than the sine theta. It's going to be probably more spiky, but again, it's going to be symmetric. And again, the area on the top and bottom, it's going to cancel each other. There are many different ways you can show that, but this is just arguing physically. So therefore, this integral is also 0. So therefore, there is not going to be any force in the y direction. There's not going to be any so-called lift on the cylinder, and that's expected, right? I mean, cylinder is symmetric, and it's based on our experience, there is not going to be any lift on the cylinder. But how about drag? How about the force in the x direction? So let's calculate force in the x direction. So F x hat. So that's going to be negative. Well, we don't need, actually we don't have negative because this component of the force in the x direction is also in the negative direction. All right. I can move the schematic a little down so that as we do the calculation here, you can see it better. Let's just move it here. All right, so again, the direction of this force is in the negative direction of x. So I put a negative sign. Negative integral from 0 to 2 pi of p ds times cosine theta. Very similar to the other case. Everything is the same. The only thing that is different is instead of sine, I have cosine. So therefore, I can just borrow the expression from here. So this is going to be negative 1/2 rho a integral from 0 to 2 pi of u2 minus sine 2 theta u plus k over a squared to the power 2 times cosine theta d theta. And then this is negative 1/2 rho a integral from 0 to 2 pi of u2 cosine theta d theta minus integral from 0 to 2 pi of u plus k over a2 sine 2 theta cosine theta d theta. All right. Well, again, similar to the other case, the integral of cosine theta d theta, cosine theta goes from 1, negative 1, and 1. And this area is going to cancel out this area and this area. I'm confident. If you have any doubts, just do it. Just write down. I mean, the other way is easy, right? So u2 is constant. So if you want to be more analytic, I can just bring the u2 out. So that's going to be u2 integral of cosine theta d theta going from 0 to 2 pi. What is integral of cosine theta d theta? Well, that's going to be sine theta going from 0 to 2 pi, and therefore that's 0 minus 0, so 0. So therefore this is 0. And then integral of sine 2, this is the coefficient is constant. Integral of sine 2 theta cosine theta d theta is sine 3 theta divided by 3, right? And again, going from 0 to 2 pi, that's going to be 0, 0. So therefore, this is going to be 0. So therefore, the total force on the cylinder in the x direction is also 0. Does this make sense? Well, no. We expect if we have a tower under the wind or a bridge column and there's a river, we definitely expect a force in the x direction. How can we get 0? One of the earliest people who derived this solution was D'Alembert in 1752. I don't know if he was the first one, but he basically writes, maybe I make this a little larger. He writes that it seems to me, and he was of course very excited about getting this this analytical solution to the fluid flow about the circular cylinder. Probably before the last step, he thought that he saw all the problems in the world, and in fact that would have been the case because it's a very important problem. But then he gets 0 velocity, 0 force, 0 drag force, and that's basically very disappointing. It's like I was looking to calculate the horizontal force on a cylinder under the wind and current, and then I'm getting 0. So something is wrong. So this sentence is due to D'Alembert, and that's 1752. And he says, it seems to me that the theory, potential flow theory he's referring to, developed in all possible rigor. Right? He was very happy about everything is so perfect, gives at least in several cases, including for a cylinder, a strictly vanishing resistance. A singular paradox, which I leave to future geometers to elucidate, right? So he gets very, of course, upset and calls it a paradox. Then many other people, famous people in hydrodynamics, physics, and mathematics worked on this problem, but they couldn't solve the paradox. Again, the issue is, looks like we're doing everything perfect. In mathematical theory, everything is perfect mathematically, and then we get a zero resistance on a cylinder. So Euler tried to solve it in 18th century, unsuccessful. He couldn't explain what's happening. Laplace, 19th century, Cauchy, 19th century, Poisson, 19th century. They are like great minds of those eras, worked on this problem, and they couldn't explain what happened. So it stays there as the so-called D'Alembert paradox. Until Prandtl, 1904, basically pretty much explained that it's because of viscosity. All the resistance that we see on a cylinder is because of viscosity. In fact, that's perfectly true. If viscosity is 0 and we don't have any skin friction, then there's not going to be any force on the cylinder. And that makes sense because everything that, well, we have a stagnation point here, we're going to have another stagnation point on the other side. The pressure here is the same as pressure on the other side. So if the pressure balances, then there's not going to be any net force. And there's no friction, so absolutely nothing. Now, in the presence of friction, what happens is that, first of all, we have a skin friction, right? The fluid is going this way, so it pushes the cylinder back. And then there's something very interesting, something else very interesting happens for cylinders at a higher Reynolds number, and that's called separation. A fluid flow basically separates from the surface. It can't follow the surface anymore, and separation occurs where skin friction vanishes. As you can see, there is no skin friction here at this point of separation, and where flow admits an adverse pressure gradient. So we're going to have a streamline separating or emanating from the surface, and there's going to be an area of vorticity here and another area of vorticity here. This area is very low pressure, so then the pressure is not fully recovered on the downstream of the cylinder. Basically, what I'm saying is that pressure here is higher at the stagnation point. Pressure on the other side is very low, and this imbalance of pressure results in the maximum or the most major part of the force on the on a circular cylinder. And that problem, of course, with the viscosity and everything included, is a very difficult problem. As of today, we don't have analytical solution for this. In fact, there are many different regimes. We're going to talk about this in the next video. But then we have to rely on, therefore, in fact, we have to rely on experimental results and numerical results. So there's no really analytical solution. Still, the solution of D'Alembert for potential flow is a very beautiful, mathematically rigorous solution. It's fantastic that we already have this one. For many problems, we don't even have this potential flow solution in a nice compact form. But it doesn't explain everything. In fact, it doesn't explain most of the thing that we're interested in a real life application. So D'Alembert paradox, and then we're going to talk about how to include the effect of viscosity at the next level.